All right. We dealt with different types of functions in regards to the first section, dealing with domains and ranges and listing quadratic functions, inverse variations, direct variations, linears, different types of functions. Well, this course is the trigonometry course, and in the trigonometry course, we deal with what is called a periodic function. A periodic function. Your sine curves, your cosine curves, these are all called periodic functions, tangents, and we'll go into reciprocal functions also. These are all periodic functions. When you talk about a periodic function, there are function values or y values that will repeat over a certain period of time or over a certain domain. Your y values will repeat themselves over a specific period of time or over a specific domain. Okay, and this is called a periodic function, repeating decimals. We'll go through some examples here in a second. But your y values, your domain value, or your range values will start to repeat themselves. Some examples, you don't have to write all these down, but some examples, write one down or two. Repeating decimals, cycles of the moon. You have full moon, last quarter, first quarter, new moon, full moon, and you have a complete cycle that you go with respect to the moons. Ocean tides, high tide, low tide. Every 11 hours it is shifting from high tide to low tide. If you go to the oceans, you have a shift of the tides. Time, hours, minutes, and days. Okay, Mickey's second hand up there continues to repeat itself. His little hand, his big hand, they all continue to repeat themselves. They'll go over a specific pattern. The sunrise and sunset every 4 years. Okay, you have a periodic function. They'll be the same every 4 years on specific days. So these are just examples of what you have with respect to periodic functions that we live in our life. Now, when you were in geometry, you had a definition of an angle. An angle is formed by two rays connected at their endpoints. You get the Ray brothers. You got Jimmy Ray and Earl Ray. You got the Ray brothers. They're connected at their endpoints. This which is how we define the ray. We had one ray, then we connected at the endpoints a second ray, and we determined an angle. Two rays, the Ray brothers connected at the endpoint. This was an angle. But the problem you had in the geometry world was you're bounded by two values. Your angles was anywhere between 0 and 180 degrees. You can have a 0 angle or you can have a straight angle. And you're bounded by 0 to 180 degrees. In the trigonometric world, we change our definition of an angle. We still keep the same philosophy of the idea we're looking at rays. But in trigonometry, we now change this definition. This definition now becomes an angle is used to measure the amount of rotation of a ray. The amount of rotation of a ray. can add that to it there. We're rotating about its end point. Okay? We're holding the end point and we're spinning it around. That's like Mickey's big and little hand on the clock. We hold at the corner, at the middle there, and we spin it around. That's what we're going to be doing here. We have to have an initial side. It's the location of the point at which an angle will start its rotation. You have to have an initial ray there. Once again, you can pick any of the Ray brothers. Jimmy Earl, Billy Ray, any of the Ray brothers. So here's an initial side. Then we have a terminal side. And hopefully your logic in your brain will tell you the terminal side is where we stop. Okay, it's the point at which the rotation of the angle stops, so the ray stops. So you need to have an initial side and you need to have a terminal side. You have a place where it starts, you have a place where it stops. So we have this ray here, initial side here, and we're going to rotate it about its end point. So our amount of rotation here is the angle. This will be the terminal side. So we have the initial side, we have the terminal side where it stops. And this amount of rotation that we have here is called an angle. This is an angle. We've rotated from here to here. Now, with trigonometry, we are not bounded by any specific values anymore. Our angle rotation, once again, we have symbols that we use for this angle rotation. The most commonly used one is the first one, which is a circle or a zero with a line through the middle of it. This is called theta. These are all Greek symbols. Getting close to college, you need to start learning Greek symbols. You need to know fraternities and sororities. This is theta. This is alpha, looks like an A. And this last one here is beta. These are the most commonly used ones. I use theta quite a bit. But when I need the extra ones, I'll throw alpha and beta in there. Once again, you need to start learning Greek symbols. We can put an angle in a standard position. The vertex of the angle is at the origin, or the end point of the ray. You want to think of it that way. The end point of the ray or the vertex of the angle is at the origin. So we're going to hold this ray at the origin, the end point, and we're going to start spinning it. And that end point is going to be at the origin. So you have the end point of the ray or the vertex of the angle is going to be at the origin. The initial side of the angle is on the positive x-axis. The initial side of the angle is on the positive x-axis. Clockwise rotation is negative. Counterclockwise rotation is positive. This goes into the idea of lefty-loosey, righty-tighty. If you're loosening a bolt, or if you're tightening a bolt or tightening a screw, okay, you have to go clockwise. That spins it down into the wood or onto the bolt. That is a negative direction. If you go righty-tighty, lefty-loosey, you start lefty-loosey, that's going to be coming out at you, and that's a positive direction of the bolt. Okay, so this goes all right into the idea of lefty-loosey, righty-tighty. Clockwise rotation is negative, counterclockwise rotation is positive. So if we take a look at an angle of 140 degrees, the initial side of the ray is on a positive x-axis. The end point is at the origin. So you have the end point of this ray at the origin. The initial side is on the positive x-axis. We're going to rotate this 140 degrees. So now we take a look at which quadrant is this going to end up in if I rotate this 140 degrees. All right, so which quadrant would this end up in? Quadrant what? 3. So if I go 140 degrees, I'm going to rotate this. This is going to go all the way down to quadrant number 3. Quadrant 2. So I'm going to rotate this. This will rotate 90 degrees. This is going to be rotating 180. So 140 is about halfway through. We don't need to have protractors here. We don't have to have exactness. We just need to be able to get a good location where it's going to be stopping. So this will be my rotation of 140 degrees. If I rotate negative 140 degrees, once again, I'm starting here, and I'm going to rotate negative 140 degrees. Which quadrant would we end up in if we rotated negative 40? Amy? Third quadrant. So I'm going to rotate, if I rotate negative 140, that means I'm going to go clockwise. That's negative 90. That's negative 180. That's going to put me into this quadrant. So it'd be negative 140 degrees. 560, where would that end up in? Draw your angle. 560 degrees, where would that end up in? Which quadrant? Seth, where did we end up in?
Quadrant 3.
Quadrant 3. If I rotate all the way around at 360, that will give us 450. This will give us 540. And this will give us 560. So that'd be your 560 degrees. We'll deal with this in a second. Coterminal angles. We talk about coterminal angles. These are angles whose terminal side will be in the exact same location. Angles whose terminal side is in the same position. Rather than rotating negative 40 degrees, what would be another angle for our rotation here? Rather than going negative 140, what would be our angle of rotation? Write it down. Check your answer with somebody around you. Rather than going negative 140, what would this be? What would be another angle we would have? Cade Miller, what do we have? 220 degrees. That is correct. Because if I go all the way around the circle, how many degrees would be the entire way around? 360. So if I go negative 140 here, okay, what's that leave over here? Well, that's 360 minus the 140, which would give us the 220 degrees here. Reference angle. We talk about a reference angle. It is a positive angle. It is an acute angle that's formed by the x-axis and the terminal side of an angle. So it's an angle formed by the x-axis and the terminal side. Okay? Doesn't matter which x-axis we talk about. It is an angle formed, it's a positive, and it's acute. I guess it could be right. Most of the time, we're going to be dealing with acute angles. You have positive and you have acute. What's it mean to be acute? Less than 90 degrees. So you're talking about smaller than 90 degrees. So if we take a look at our angles up here, okay, how we symbolize data reference is we just put a subscript there, R. Terminal side and the x-axis. Here's your terminal side, here's your x-axis. This is your reference angle. What would be the measure of the angle between the terminal side here and the x-axis? Our rotation was 140 degrees. What would our rotation be, Justin? 40 degrees. Okay, it would be 40 degrees. Go ahead and find the other two reference angles. Check your answers with somebody around you. What would be the other two reference angles? Once again, check your answer with somebody around you.
What? It should only be the
Okay, but what do you have for the first one?
40.
40 degrees still. Okay, terminal side and x-axis. Common mistake here is you'll throw a negative in with this because I've rotated negative 140 here, and then you want to throw the negative in with that. That's incorrect. It's a positive angle. So even though you might sit there and say, well, that's a negative 40 rotation, it's going to be the positive angle. We just want the absolute value of that if you want to think about it. We just want absolute value. 560, what do we have with 560? Okay, Mullet? 20 degrees. That is correct. Now, you can think of this a bunch of ways. We can go, this was, if I go all the way around, that's 360. That's 450. That's 540. Okay, so you can count by 90s to get to that point. So that's 360, 450, 540, 560 gets me another 20 degrees. So this angle here would be 20 degrees. Okay, counting by 90s is not a bad deal. Let's see, 1240. Find the next two. Check your interest somebody around you. 540 and 7,650. See if you can figure out a way that might be a little bit easier to calculate your reference angles. Okay, in all these problems, the best thing to do is draw a picture, draw a picture, draw a picture. Where does the terminal side end up at? Where does the terminal side end up at? And then go from there. Figure out where the terminal side ends up at, and then figure out what your reference angle is. 1240. Where does it end up at? What, Carson?
Quadrant 2.
Quadrant 2. You know that? Okay, now how'd you figure that out?
I did a whole bunch of circles.
Okay, did a whole bunch of circles because each circle adds up to what? 360. So he spun around here. Okay, we had one circle, 360, second circle, 720, third circle, 1080. Okay, so that's 1080 going 3 circles. That gives us 1170 or 1170. That gives us 1260. So we're at 1240 in there. So we just did a bunch of circles here to end up there. Okay, what is our reference angle? What'd you get then?
I got
20 degrees. Terminal side and x-axis, 20 degrees. Okay, every time you go around is 360 degrees. Anybody figure out an easy way to do this?
Divide by 360.
Okay, so we take 1240 divided by 360. That gives us 3 and some change. Okay, 3 and some change. We don't know what the change is there. You can have it in your decimal point, but if I have 3 and some change, 3 times 360 gives us 1080. So if I go 3 times around, that gives me 1080. Well, how many more degrees do I have to go to get to the 1240? I can take the 1240 and subtract off the 1080. And that would give us 160 degrees. That will get us there and get us our reference angle. If I take the 7650 and divide that by 360, that tells us how many times I'm going to spin around. Okay, if I take 7650 divided by 360, how many times would we spin around? Courtney? 21 times. Okay, so if I look at my axes, if I have 7650, I'm going to spin around. Whoopsie. That was crazy. 21 times. 3, 4, 5, 6, 7. And I'm back there again. So if I take the 21 times my 360, how many degrees is the 21 times 360? Ava?
7,560.
7,560. And I'm still back at the beginning. Well, how many more degrees do I have to go then? 90 degrees. So I have to go another 90 degrees. Ooh. Up to here. So my reference angle is terminal side and x-axis, and I have a 90-degree angle there. Minutes and seconds is the old school way of dealing with decimal points. 1 degree is equal to 60 minutes. 1 minute is equal to 60 seconds, just like a clock. The hours get replaced by degrees. So if I take a look at 151 degrees, 12 minutes, and I want to find the reference angle. Once again, getting our picture down. 151 degrees, Jared, would take us into which quadrant?
2.
Quadrant number 2. So I'm going to go into quadrant number 2 here. My reference angle is the terminal side and the x-axis. What would we have to do to find our reference angle? I have 151 degrees, 12 minutes. What would we have to do? Courtney? What would we have to do to calculate this? I rotate 151 degrees, 12 minutes. I want to find this angle here. What do you think we should do? what would you, don't do calculations yet. Just- Anybody, what do we have to do here? 180 minus 151, 12 minutes. Now, if we need to subtract this, it's like if I had a value of 11 minus 3.7, and I was dealing with decimals, I didn't have a calculator. What would we have to do to subtract 11 minus 3.7? Anybody remember mathematically what we did? 5th grade math, 6th grade math. We added a decimal point and a 0. And then what do we have to do? We had to borrow. So this came down to 10, and this came down to 10 here. And then we could subtract. Well, it's the same thing we do here. We have 0, 0. We borrow from 180, making it 179. That makes us what? Not 10. 1 degree is equal to 60 minutes. So that turns into a 60. So now I can subtract down 60 minus 12, 48 minutes. And then I can subtract the rest here. 28 degrees, 48 minutes. Bells are turned off. Adios, folks are out of here. Yep. Homework's on the back. It's also on Classroom, page 13. 1 to 33, the odds. Next time, draw a picture, draw a picture, draw a picture. Page 13, 1 to 33, the odds. Have a good day.